In section 5.3, we're going to discuss properties of logarithms. Below is a list of the fundamental properties of logarithms. The first one is what's referred to as the product rule. Let b, m, and n be positive integers such that b is not equal to 1. Then the logarithm base b of the product m times n is equal to log base b of m plus log base b of n. Okay. A couple things to keep in mind when it comes to the product rule for logarithms is that we're about to get in total, there will be three rules for logarithms. And every one of these rules for logarithms that we get come from a corresponding property or rule for exponential functions. Okay. For example, we might recall that, when you multiply by like bases, we add the exponents. Kind of similarly here too. If you see a log of a product, where this on the left-hand side is a single log, where the multiplication of the product is taking place inside the log, this can be split apart as the sum of two separate logs. It's log base b of m plus log base b of n. The second thing to keep in mind is anytime we have an equality, there's two sides to that equality. And sometimes what we're going to want to do is we want to expand, which would mean to starting with the product, we would write it as two separate logs of the sum. On other times, we might want to condense this, go in the other direction, where if we have the sum of two logs that are the same base, we can write that as a single logarithm of a product of their values on the inside. Okay. Let's take a look at example 1. The directions simply say to use the product rule to expand each logarithm. So in example A, it's log base 4, and we have the product of 7 times 5 on the inside. According to the product rule, this can be turned into log base 4 of 7 plus log base 4 of 5. In part B, we want to expand common log. So remember, there's no base that's explicitly written here. So this is understood to be common log, that is log base 10 of 10 times x. So again, when you see the 10x, implicitly, that means 10 times x. So it really is a product. So we can write this as the common log of 10 plus the common log of x. And we can actually do one better than this, because if you remember from the previous section, this value simplifies. Log of base 10 of 10, that's equal to 1. Again, common log of 10, that's asking what exponent would you need to raise 10 to in order to get 10 to the first? Well, that's equal to 1. The next property is what's referred to as the quotient rule for logarithms. Let b, m, and n be positive numbers with, again, b not equal to 1. Then the log base b of the quotient of m divided by n can be written as log base b of m minus log base b of n. So kind of by analogy, if you compare the quotient rule to the product rule, on the product rule we were multiplying on the inside, and that turned into the sum of two logs. Well, the opposite of multiplying is dividing, and similarly the opposite of adding is subtracting. So when you look at the log of the quotient, it's the difference of the two individual logs. And when you split it apart, again, the order is very important here. It's log base b of the numerator minus log base b of the denominator. Let's use the quotient rule to expand each one of these expressions. In part A, it's log base 7 of 19 divided by x. This is going to be log base 7 of 19 minus log base 7 of x. So we've expanded it. Let's take a look at part B. In part B, we have the natural log of e cubed divided by 9. That's a quotient. We can write that as the natural log of the numerator minus the natural log of the denominator. This one, too, can also be simplified a little bit further. If you look at the natural log of e cubed, recall that the logarithm base e, which is the natural log, and the exponential function e to the power b are inverse operators. So the ln of e cubed, if you want to, you can think of the ln as e is canceling, and so this would just reduce it simply 3. So we get 3 minus the ln of 9. The last rule for logarithms that we're going to deal with is what's called the power rule. Let b and m be positive numbers, again, b different from 1, and let p be any real number exponent. Then log base b of m raised to the p power is equal to p times log base b of m. In essence, what this rule is stating is that if you have an expression on the inside of a logarithm, and if the whole thing is being raised to an exponent, then we can take that exponent on the inside of a logarithm and bring it out in front as a multiplication. Let's use this power rule for logarithms to simplify each of the resulting expressions. The first one we have is log base 5 of 7 to the 4th power. So we have an exponent on the inside of the log. According to the power rule, we can bring that out in front and write this as 4 times log base 5 of 7 like this. If we take a look at part B, we have the natural log of the square root of x. It might not look explicitly like there's an exponent here, but recall the square root is equivalent to x to the 1/2 power. And then again, same thing. If you have an exponent on the inside of the log, we can bring that out in front as a multiplication. So this is equivalent to 1/2 the ln of x. And now let's take a look at part C. In part C, notice that we have common log of 4x to the 5th. The entire expression on the inside is being raised to the 5th power, so we can bring that out in front as 5 times log of 4x. Now for this part, if we wanted to, we could actually do more with this piece, because we would actually be able to now apply the product rule if we wanted to split it apart even further. Let's go ahead and do that. This is some common arithmetic that you're going to see in this section, but notice that when we use the product rule for logarithms, this is 5 times the log of 4x. If we take and we split log of 4x into more than one term, it's important to realize that that 5 must multiply to whatever that result is. So this is going to be common log of 4 plus common log of x like this. And then if you expand it, you can distribute the 5 in, or you can leave it out. But this is what we would get. And again, not only were we able to use the power rule for logarithms in this last example, but then once we did that, we saw what resulted with the product rule, so we could split it apart even further. And again, take notice of the use of parentheses here. Both of those terms, when they get split apart, need to get the multiplication by the number 5. As the last example kind of showed us, a lot of times if we want to go through the process of expanding a logarithm, we might be able to apply more than one rule at once. Okay? So to expand a logarithm means to expand it into a series of individual log terms. If we take a look at example 4a, we're asked to use properties of logarithms to expand each expression as much as possible. If we look at what's going on with example A here, we have log base b, and on the inside it's x squared times the square root of y. Well, that's a product, so we can use the product rule for logs that says that we can split this into 2 logs. It's the log of the first factor, log base b of x squared, plus the log of the second factor, log base b of the square root of y. So that's the first step. That was simply using the product rule for logs. Now that we're here, we see that implicitly, each one of these is being raised to a power. We have x squared here, which is pretty explicit, right? The power is 2. But remember that if you have the square root of y, That's the same thing as y to the 1/2 power. So we can take and bring each one of those exponents down in front by using the power rule for logs. I'm just going to rewrite the second part so we see it. It's y to the 1/2 power. According to the power rule, we can now take each exponent out in front as a multiplication. And then what we're left with is the following. The first term is 2 times log base b of x plus, now we have 1/2 times log base b of y. And that would be our final answer. We have just simple expressions left on the inside of the logs where there's no more operations, no multiplications, divisions, or exponents that we could do anything further with. So starting with the beginning expression, we were able to use property of logs to expand it into this bottom expression. Let's do the same thing for the next one. We have log base 6 of the cube root of x divided by 36y to the 4th. At its heart, the fundamental operation on the inside is division. So we're going to use the quotient rule for logs. The quotient rule for logs says it's the log of the numerator subtracting the log of the denominator. So we applied the quotient rule to expand it. The next thing we would notice is that this second term that we have here, log base 6 of 36y to the 4th, that's a multiplication, that's a product. It means 36 times y to the 4th, so we can use the product rule on the second term. When we do that, let's be very careful here. This term is being subtracted. If we go and split this second term up into more than one term, we have to make sure that we're subtracting everything that's a part of it. According to the product rule, this would be log base 6 of 36 plus log base 6 of y to the 4th. From here, let's go ahead and distribute that negative sign through. So this would be minus log base 6 of 36, and then minus log base 6 of y to the 4th. And now we're ready to do the final simplification. Log base 6 of the cube root of x. Recall that the cube root of x is the same thing as x to the 1/3 power. So we can bring that power down out in front of the log using the power rule for logs. This would become 1/3 log base 6 of x minus this term in the middle, log base 6 of 36. That's actually an exponent that we can figure out. Log base 6 of 36, what that is that's the exponent we would need to raise 6 to in order to get the value 36. Well, 6 squared is 36, so this is going to be 2. And then minus, again, we can use for the last term, we can use the power rule, bring that 4 out in front as a multiplication, and we get 4 times log base 6 of y. And now we have totally expanded that second expression. One of the kind of shortcut tips that I like to advise students when it comes to expanding logs is when you're expanding this log, we have 3 terms that are here. If you want to think of it as like products, we have like a cube root of x, a 36, and a y to the 4th. If you think of how the quotient rule works, any of those factors that were in the denominator will ultimately in the final answer have a subtraction sign because of the way the quotient rule works. It's log of the numerator minus log of the denominator. So the fact that these 2 factors were in the denominator should lead us to having negative signs for their terms when we expand them. Any term that came from a numerator of a quotient in a log will actually end up with a positive sign. Again, just kind of thinking about how the quotient rule works. Now that we know how to expand logarithms, we're going to do the reverse process, which is going to be condensing logarithms. So starting with a collection of individual terms, we want to see if we can combine them and condense them into a single logarithm. Okay, so this is kind of like working backwards. In example 5, we're asked to write as a single logarithm. It's going to be log base 4 of 2 plus log base 4 of 32. Here we have the sum of the two logs, where there's no coefficients out in front, and it's the same base. So we can go right to the product rule in reverse. This is going to be log base 4, and then it'll be the product of the values inside. So this is equal to log base 4 of 2 times 32. And 2 times 32 we know is 64. And we can do a little bit better on this because we know that 4 to the third power is 64. Therefore, log base 4 of 64 equals to 3. If you do 4 times 4 times 4 3 times, that gives us 64. And that's why log base 4 of 64 is 3. Let's take a look at the next one. We want to condense these. Notice that these are both common log. We have common log of 4x minus 3, subtracting common log of x. Because there's no coefficients out in front, we can just go directly to the quotient rule. The quotient rule says we can write it as a single logarithm of the quotient of the first value, 4x minus 3, with the second value, x. Let's do another one. Let's take a look at example 6. We want to write as a single logarithm each of these. If you think about the steps that we had back when we were expanding, one of the last steps we had when we were expanding was we oftentimes had to use the power rule when it was present. Well, if we're going to condense now and write as a single logarithm, that last step that we did previously, we want to undo first. So if you have any coefficients that are out in front of a logarithm, the first step would be to use the power rule to bring those coefficients to the inside of the log as an exponent. For example, 1/2 common log of x, we can write that as log of x. The 1/2 can come inside as now an exponent for the x term. Plus, similarly, this is going to be common log of now x minus 1, where that quantity is going to be raised to the fourth power. We've now cleared off the coefficients that were in front. We have the sum of two logs, so we can use the product rule to write this as a single log, and then what would go inside of that single log would be the product of x to the 1/2 and x minus 1 to the fourth. And now we have it nice and condensed. You can leave your final answer like this. If you prefer to have the square root instead of the x to the 1/2, you can do that as well. Okay. But this is our final answer. We've taken what was 2 logs in the beginning, and we were now able to condense them and write the answer as just a single logarithm. It's the log, and on the inside we have the product of the square root of x with x minus 1 to the fourth. Let's take a look at the next one. Again, to start off, what we want to do is let's bring each of these let's bring each of these factors on the inside as an exponent. That's the power rule for logs. This is going to become the natural log of x to the fourth minus the natural log of 6 squared minus the natural log of y to the 1/2. And before I do anything else, let me just kind of go ahead here and simplify a little bit. We know that 6 squared, that's simply the number 36. And I have the preference, I tend to like it to write it as a square root of y. So I'll write y to the 1/2 as the square root of y. Now from here, there's a couple of different ways you can do this. We obviously want to kind of condense these into a single log, and I'll show you 2 different ways to do this. One way would be to kind of follow order of operations. If you were to subtract these, notice we'd have to go from left to right. So the first step would be to do the ln of x minus the ln of 36. So I'm going to do an associative property type thing where I group the first two terms together. According to the quotient rule, this is going to be equal to the ln of the first value divided by the second value. So these two combine into a single log. It's the ln of x to the fourth divided by 36. And now this is going to be subtracting the ln of the square root of y. We can once again use the quotient rule. This is going to be the ln of what goes in the numerator is the first value. That's x to the fourth over 36. And what's going to go in the denominator is going to be that square root of y. Notice that we can't quite leave our answer like this because this is a complex fraction. So you would want to rewrite this. We have x to the fourth divided by 36, and we're trying to divide that by the square root of y, which you can think of as the square root of y over 1. So to divide, we know that's the same thing as keep, change, flip. So division becomes multiplication by taking that second term and doing a 1 over. And this is what we get. It's the ln of x to the fourth. And in the denominator, we have 36 square roots of y. So mathematically, that's kind of how it works out if you follow the rule strictly. There's another way, though, that you can kind of handle this. And this is a kind of a shortcut trick I like to teach my students when it comes to working with these kind of logs. And that's the following. When you get down to this step here, where you have a bunch of different log terms of the same base that are either added or subtracted, a fast and convenient way to write that is you know that you're going to have a log with some kind of quotient on the inside. The shortcut technique is this. Any value that has a positive sign on the out front, that value will end up in the numerator of your final logarithm. Any of the values that have negative signs out in front of them, those will be values that will end up in the denominator of the log. So if you're aware of that, and if you pay attention to that or do enough of these, you'll see that that pattern holds true, and in which case you can go right from this step to the final answer without having to do it step by step and avoid the cumbersome problem of having to deal with complex fractions. The last thing we're going to talk about, and this is especially important if you need to do any kind of computation, is what's referred to as the change of base formula. Okay? According to any positive value b different from 1, we get a different log function. Yet if you look at the calculator, most calculators only ever have two buttons. They have the common log button, which is log base x, and then they also have a natural log button, which is the ln of x. So then the question would become, well, what if you wanted to evaluate something else? Like, what if you wanted to evaluate, in the next example, we're going to look at log base 5 of 140. How would we compute that? Well, the answer is there's a change of base formula. Okay? Given any bases a and b, you can always convert from log base b to log base a by doing the following thing. Log base b of m is equal to log base a of m divided by log base a of b. Okay. And I'll actually derive this one. I don't really do a lot of derivations in this class, but this is one. Let me actually show you how this works. So let's suppose you wanted to plug something into the calculator, and maybe this base b is one you're not really familiar with. Okay. Whatever this value is equal to, remember, we can go ahead and change it to an exponential form. Log base b of m is equal to an unknown, means that if we take b to that unknown power, that should give us the value m. The idea is that if there's a base that's more convenient, let's suppose that a is a base that we prefer, what we can do is we can take log base a of both sides. So I'm going to take log base a of both sides of this equation, and I get this. Log base a of b to the unknown is equal to log base a of m. According to the power rule for logs, I can take that unknown exponent, bring it out in front as a multiplication. So the unknown exponent times log base a of b is equal to log base a of m. And then to get the unknown value by itself, all you're simply going to do is divide both sides by log base a of b. Divide by log base a of b, cancels, and that's where that change of base formula comes from. It turns out that, again, we want to use bases that are easy to work with. So for us, a is almost always either 10, common log, or ln. And it doesn't matter which one you do. But for example, if we wanted to use logarithms, common logs to evaluate log base 5 of 140, according to the change of base formula, this would be equal to, in the numerator, it's the log of the value on the inside. So this is going to be the log of 140. And then divided by, in the denominator, you have common log of the base. So this would be common log of 5. This would be the exact answer. If I plug this into my calculator, I'm just going to say it's approximately equal to, I'll round it to 2 places. This is approximately 3.07. Let's show we would get the same thing if we instead used natural logs. Well, if we did log base 5 of 140, again, according to the change of base formula, this would be equivalent to the ln of the value divided by the ln of the base. So this would be the same thing as the ln of 140 divided by the ln of that original base, which is 5. And if you test this and if you plug it in, you're going to get the exact same approximation. It's the same number. It's 3.07. And it's exactly because of that change of base formula, which is why the calculator does not need to have logarithms for different bases. As long as you know the log values for one value, we would be able to calculate, according to the change of base formula, the logarithm of any base of any number. Okay? It just so happens that both common log and ln are so popular that calculators will tend to include both of them.